Uh, so far in your security course, we have discussed various classical ciphers. We have discussed the classical ciphers. Then we discussed symmetric ciphers. Then we discussed asymmetric ciphers. Okay. We know what are various classical ciphers we have. We have seen various symmetric ciphers, including DES, triple DES, double DES, then AES. Then in asymmetric, we have discussed popular algorithms like RSA, Diffie-Hellman, ElGamal. Then these asymmetric algorithms we discussed. And in addition, we also understood the importance of key management and distribution. When we say key management and distribution, it includes both symmetric keys and asymmetric keys. How to share, how to establish the symmetric keys, how to distribute asymmetric keys. These are the things we discussed in the sessions, various sessions. Now onwards, we will focus on hash functions, the cryptographic hash functions. We discussed what are the hash functions, what is their role, why do we need all that. Remember, when we discussed these symmetric algorithms and asymmetric algorithms, our goal was to maintain confidentiality, right? We also focused on integrity. In some occasions, we were focusing on authentication, right? So these were the various goals that we were targeting it. So confidentiality. We also said integrity, but if you notice, predominantly our discussion was focused towards confidentiality. Okay, how to maintain confidentiality of the data. Is it that we cannot achieve integrity with the cryptographic algorithms from symmetric and asymmetric? Of course, we can achieve integrity. But remember, there are applications which are focusing on purely integrity. So integrity only. Our focus was, imagine if there are applications that were focusing about only the integrity. That means, look at the scenario. Alice and Bob. Alice is sending a document to Bob. Okay. Alice is sending a document to Bob. Imagine the scenario. Alice is not worried about confidentiality, right? So he is not worried about confidentiality, but he is worried about during the transit, during the open communication channel, if the document is getting tampered. Okay, so that is the integrity problem. So Alice is worried about the document integrity. So how to ensure that when Alice is sending a document to Bob, again, I repeat, Alice is not worried about confidentiality of the document. Right? So take an example. We distribute our marks. When we distribute our marks, what would be our focus? Hello? Whether we would be worried about confidentiality or integrity?
Integrity.
Imagine if we are talking about the question paper of the examination. What about that? Security for question paper. What we concerned about? Essentially confidentiality, but also integrity. But look at the marks scenario. Imagine we are maintaining a database of marks of all the students. Our focus would be on confidentiality or integrity. Essentially, it is integrity, right? We don't want somebody to hack into our database and tamper the marks. That is the integrity problem. Similarly, there are n varieties of applications in the real world scenario where you don't actually worry about confidentiality, but what is worried is you are worried about integrity. Now, how do I ensure that when I have such type of applications where integrity is the only concern, how do I focus and ensure that the document, the data, the message that is sent from the source to the destination or that is stored in a database, integrity is maintained? That means the contents are not tampered. How do I do it? Of course, the point is somebody may say that, look, sir, I can achieve it the integrity through encryption, right? I can perform encryption. So, of course, you can perform encryption. And when you encrypt the data, obviously somebody cannot tamper it. But there is a bottleneck there. We will discuss that bottleneck little later. Now, the point is, Alice is sending a document to Bob, and the only concern is about the integrity. Now, for that purpose, what Alice wanted to do is that, look, I'm sending you a document. So he is sending a document to Bob. What Alice is doing, Alice is sending the document plus some code. Okay, that code was originated, the code was created based upon the content of the document. Okay, based upon the content of the document. Imagine there is a code that was generated based on the content of the document. So Alice is sending both the document and code to the Bob. Okay, Alice is sending both document and code. Code is created based on contents of the document. Okay. Now, document plus code are sent to Bob. Now Bob would receive it. After receiving the document and code, Bob would calculate the same code on the document what he received. Now he checks that particular code what he got on the document and the code that was received from Alice. If both are same, that means the content of the document is not tampered. The integrity of the document is not lost. Hope you got the point. I repeat, Alice is sending a document. While doing it, he created a code. Now Alice is sending both document and code to Bob. Bob receives this and calculates the code on the document what he received. He compares whatever the code the Bob calculates. So he calculates code and he compares that code with the code that what he received. If both are same, that means content is not tampered. I hope all of you are able to follow this. Is that clear?
Yes,
Hello?
sir.
Any doubts here?
No, sir.
But the point is, you may get a doubt, sir, why all this calculating code and all that? Instead, let Alice encrypt the document. So perform encrypt and send it to Bob. Now, no one can tamper the document because it is encrypted. Why you are performing this calculating code and all that? The problem here is why we are looking at the other codes. What we discussed here about document plus code is, of course, I can achieve the same integrity by performing encryption. But there are different aspects to it. Number one, encryption algorithms are generally, we all know that they're computationally intensive, right? Whether it is symmetric or asymmetric, they're computationally intensive. Of course, asymmetric are much more intensive than symmetric. And another thing, if you look at the scenario what I have narrated here, document plus code scenario, Was there any calculation of decryption, performing the decryption? There is no decryption. The decryption comes only when you encrypt. So that means you have the bottleneck of performing the decryption also if you encrypt. But look at the case where what we have done here. Document, code is generated at the sender side, code is generated at the Bob side. So that means your code generation algorithms are typically less intensive code generation. We will see what is that code. So when compared with your typical encryption algorithms, your code generation algorithms are computationally less intensive. The simple logic is that you don't even have the you need to have to perform the decryption also. Imagine if it is a DES algorithm, you have to perform 16 rounds of operation of encryption and 16 rounds of operation of the decryption, right? So like this, you have various bottlenecks. Similarly, when it comes to perform encryption with the help of asymmetric algorithms, we already know that they are more computationally intensive. In addition to that, they have another bottleneck of establishment of the keys, right? How do each other knows the public key of the other node? That itself is another problem. Of course, we discussed that in the previous classes. So these are all the reasons why when it comes to addressing the integrity. So when we wanted to address the integrity alone, okay, integrity alone, we don't go for no encryption. That means, we don't go for encryption, but instead we go for hash algorithms, okay, or hash functions. I hope you got the point. Is that clear? Hello?
Yes.
Hello, yeah.
Yes, sir.
Is that clear? So what is this hash functions are doing? Typically, the hash functions, if you notice, they take a variable length input. Okay. So the input would be of variable in length. So if you look at the Alice to Bob scenario, Alice is sending a document. The document could be of any length. The document could be of any size. But the hash function produces a fixed length output. That output is called as digest, or it is also called fingerprint of the document. So the hash function is taking a variable length input, producing a fixed length output. The output is also called as digest or fingerprint. Okay. So the point is the hash functions are having no key. Okay, look at your symmetric algorithms or an asymmetric algorithms where they are basically either single key or multiple key. But whereas the hash functions, you don't have any key algorithm. That's the reason why they are also called as keyless ciphers. Okay, because there is no key at all. And remember, as we discussed a few seconds back, you only perform calculation of the hash functions. That's all. And hence, there is no, since there is no encryption, there is no decryption as well. Right? So there is no decryption. You only perform calculation of the hash. There is no decryption. First of all, we need to say there is no encryption at all. So it's only performing the hash. And remember, you always do only in this direction. You notice the input of variable length message producing fixed length output. You never try to do this other way around. Whereas in the case of an encryption algorithm, so what is needed is when you take the encryption algorithm, you give the message, you get the cipher, right? But when you give the cipher, you are supposed to get the message, right? Hello? Hello? Hello?
Yes, sir.
Yes, sir.
Okay. Yeah. Okay. Again, see, on a lighter side, I'm just telling. Okay. Who are all there from? How many students are there here in the session? Do you have any placement related activity going on from the CDC side? Like yesterday
No, sir.
orientation. Sorry?
Yesterday from the
Today
CDC
we
we
had
have
our
the live
orientation.
section on the placement recruitment, sir.
Okay.
Yesterday.
Today any such? Today
Today,
any activities going on?
not there, sir. Not there.
Okay. Yeah. Our quota Nikhil is there.
Also, sir, but we have hostel room counseling from 9:30.
What time?
9:30
9:30.
p.m.
What is
9:30
that?
a.m.
What is that activity?
Hostel room counseling.
Hostel booking.
Hostel room allotment. Okay. This is for the current this semester or for the next semester?
Current semester, sir.
Okay. So that means for those when you are returning back for that purpose, right?
Yes, sir.
Okay. Understand. Okay. No problem. So if you notice the hash functions, okay, let me put the image here. So if you notice for a hash function, so this is the hash function. Input can be of any length, so variable length input. Okay. And that produces fixed length output. So if you notice, there is a message, plain text message. When it is submitted to a hash function, it is producing a fixed length output. Okay, so imagine this particular hash function is of say 512 bit. Obviously, the output would be of 512 length. Irrespective of your length of the message, you are going to get the message digest of or hash value of 512 bit. Okay, similarly, if you notice, output is sensitive to all input bits, and remember, it is exhibiting a strong avalanche effect. I don't know how many of you recall that about avalanche effect. We talked about this during the DES algorithm. So even a minor change, even a single bit change in the input, that produces a major change in the output. So if you notice, there is a message called I am not cook, and there is another message called I am not a cook. Okay, so you can notice the similarity of these two sentences, but when they are submitted to the hash function, they produce altogether different message registers, right? So the output, whatever the digest that you get, is sensitive to all input bits, and message digest algorithms exhibit the strong avalanche effect. Okay, so this is these are all the fundamentals of hash functions. So now the point is, when I have this hash function or a hash value, how I am going to check the integrity, how I am going to check the integrity of the message. So this is the typical diagram that illustrates that when you have a message, so submit that message, uh, submit that message to the hash function and create the digest. Once you have the digest, what you can do is you can send the message plus digest to receiver. Okay, so what the receiver can do, receiver receives the message and digest and check. He will calculate again the digest on the message. If the both this digest and the received the digest that the receiver has calculated, if both are same, he is going to keep the message. Otherwise, he will say that yes, the message is compromised. Okay, so that's what is the role of message digest or the hash functions in verifying or in ensuring the integrity. Okay, now there are certain important characteristics that these hash functions have to exhibit. You cannot take any function as a hash function. So a cryptographic hash function, any hash function or any message digest function has to satisfy three criteria. One is pre-image resistance, second pre-image resistance, and collision resistance. These are the three criteria that a particular hash function, you take any hash function, there are several hash functions like secure hash algorithm, there is a message digest algorithms. These are all the various algorithms that are there. These algorithms have to exhibit these three properties. Let us see what are these properties. So first let us take pre-image resistance. What do you mean by pre-image resistance? So this is the hash function. You give the variable length input X. You submit the variable length input X and you get a fixed length output which is h of X or the digest. That is what actually is the role of hash function. It gives you a hash value. Now the point is that what is the pre-image resistance is when you have the digest, it is the function should exhibit one-way property in the sense that it is always possible by giving a X calculating h of X, but taking h of X calculating X is not possible. So this is possible, X to h of X, but h of X to X is not possible. So this is called one-wayness or else pre-image resistance. Are you able to follow? Any doubt? Hello? The second property is called second pre-image resistance or weak collision resistance. What does it mean? Imagine you have a variable length message called x1 that is giving you the hash digest value or hash value or message digest value h of x1. You have an x1 and you have its corresponding h of x1. What is the weak collision resistance is having x1 and h of x1, you should not be able to find out an x2. You should not be able to find an x2 whose hash value is h of x2 and h of x1 is equal to h of x2. You should not be able to find out such x2 whose hash value is equal to the hash value of x1. It is called second pre-image resistance. I repeat, you have an x1, a message, and you have its corresponding hash value, h of x1. Once you have x1 and h of x1, weak collision resistance property says you should not have an x2 whose hash value is h of x2 and it is same as h of x1. You should not be able to get such x2, wherein which x2's hash value is equal to hash value of x1. It is called second pre-image resistance. Finally, you have collision resistance. What does it mean? Any user of the hash function should not have two messages x1 and x2 that leads to same hash values. That means h of x1 is equal to h of x2. The user should not have or should not be able to find or should not get two messages whose hash values are equal. That is called collision resistance. In fact, if you are ensuring that your hash function is collision resistance, that means it is satisfying second pre-image resistance or weak collision resistance also. Whereas if your hash function is satisfying weak collision resistance, it may not guarantee that it is satisfying collision resistance also. But whereas a hash function satisfying collision resistance is satisfying second pre-image resistance or weak collision resistance. Finally, I have to say that there are important things what you need to remember is that number one-way property, in the sense that when you give an x, you should be able to calculate h of x, but when you have h of x, you should not be able to calculate x. That means reverse is not possible. And what is the other important property? This is the one property. The other important property is no two messages x1 and x2, no two messages have equal hash values. If there are two messages having the same hash values, that means there is a collision. So hash functions should be of strong collision resistance. No two messages have equal hash values. Is that clear about the properties of the hash function? Oh. Hello here. Hello.
Yes, sir.
Yes, sir.
So let us see that these points in some images. Okay. So you can notice the pre-image resistance or one-way property is that given y h of m, calculating the hash value is possible, but having h of m should not be able to get y. Okay. Sorry, having h of m, you should not be able to get an m. That is what is having y, you should not be able to get m. That's what is pre-image resistance or one-way property. Imagine if you are able to get it. That means once if you have h of m, that means hash value of the m, the message, and from that if you are able to derive m, that is called pre-image attack. Okay, that means attack on the one-way property. Generally, if that is there for any hash function, you should not use that particular hash function. Next one is second pre-image resistance, where what we said, you have m and its corresponding h of m. Imagine if you are able to identify some n and its h of n such that your h of m is equal to h of n. That means it is weak collision resistance attack. If first of all, you should not be able to identify such n. Okay, that is called weak collision resistance, right? If you are able to identify, that means it is an attack. That means you are able to calculate some n or m dash such that h of m is equal to h of n or m dash. You know, that other case, if it is m dash, it is h of m dash. So some n which is not equal to m such that you are able to calculate h of m is equal to h of n. So it is called an pre-image attack or weak collision resistance attack. Collision resistance, you have two messages m1 and m2 whose hash values are same. In such case, this is called collision attack. What we discussed is that you should not have, if you get it, it is a collision attack. Okay. That point is clear to you guys. These are all the important properties that the hash functions should exhibit. Okay. Now, having said that, look at the scenario of the following. So you see the diagram on the screen above. Alice is sending a message to Bob. What Alice did? Alice took that message, calculated hash of the message, and appended that particular hash to the message itself. And Alice is sending that message come hash to Bob, like so far whatever we discussed. Now what Bob is doing, taking that particular data come hash block, and he takes only data part, apply the hash function. Now he get the hash value. Compare that hash value with the digest or the value that he has already received. If both are same, that means integrity of the message is not lost. Okay. That is what is the data integrity verification using hash functions. But the point is, the way this is getting implemented here is introducing an attack which we already know called man-in-middle attack. Look at the scenario. Alice is sending the message. Now the message plus hash Alice is sending. Now Bob is supposed to receive it, but Darth has captured that message come its digest. So what Darth did? Darth, instead of sending this particular data plus hash from Alice to Bob, what Darth did? Darth has inserted his own message. Darth has inserted his own message, and for that particular message, Darth has appended the hash value. So that means Alice is sending hello, and its hash of hello. What Darth did, Darth has erased that, or Darth has introduced his own data called, say, something like ping and hash value of ping. And he is sending this to Bob. Now Bob receives ping and its hash value. Now Bob calculates the hash over the ping. Bob calculates hash over ping, and he gets this output. He compares that with the hash that what he received and understands that integrity is not lost. Obviously integrity is not lost because he got the hash of ping and he's calculating hash over ping. Obviously both are same. But if you notice, Alice's message to Bob was captured by Darth. What is the problem here? Why this attack has come into picture in this scenario? Can somebody tell me? Why this attack has come into picture? Man-in-middle attack. So I understand that all of you are busy with your hostels accommodation. No issue. We will stop here. So the reason is that there is no authentication. Right? Obviously, man-in-middle attack occurs, as we have seen, either in the case of Diffie-Hellman algorithm, or in the case of Elgamal algorithm, kind of a thing. The man-in-middle attack occurs due to the lack of authentication. So you cannot implement hash functions as it is the way we discussed. That will introduce the attack called man-in-middle attack. So how to